move into another gas law, and we're going to look at gas with stoichiometry. So to help us with that, we're going to use something called Avogadro's principle. And what Avogadro's principle tells us is that the volume of 1 mole of any gas particle is 22.4 liters. Any gas particle under equal conditions, right, of any substance has 22.4 liters worth of moles. I'm sorry, worth of liters. Oof, backwards. Okay, so this is a conversion factor that you'll use a lot. 1 mole equals 22.4 liters. So it's with any substance, with any molecule, whatever it is. Okay, so our example there says 10 liters of hydrogen gas and 10 liters of oxygen gas, both at STP, contain the same number of particles. Right? That would be the same for any other gas particle. Okay, so you use this conversion to take you from a quantity of substance to a volume of substance when we start doing gas stoichiometry. Okay. One more time.
The equation, choose the others.
You could put this on your equation sheet, that conversion. Okay. Gas law, something called the ideal gas law. This is for when we have particles that we're looking at in one point in time. This is not a before and an after situation. This is for one point in time and for conditions that aren't at STP. Okay, so here's your equation. PV equals nRT. PV equals nRT. The only new things we have here are N and R. N is the number of moles. R is what we call the universal gas constant. And so that's going to be a constant, right? It's a number that's the same all the time. Okay, the R value that we will use most often is this, 0.0821. And the reason we use that one most often is because it has the other units that we like to use. Liters, atmospheres, moles, and Kelvin. Right? In order for this R value to work, 0.0821, our volume has to be in liters, pressure has to be in atmospheres, moles, and then our temperature has to be in Kelvin, right? In order for that constant to work, our units have to be correct. Okay, so that's the one that we use most often, okay, almost like all the time, dare I say all the time. You can write the other one down in your notes. I wouldn't bother putting it on your equation sheet. This R value should go on your equation sheet. I'm going to put the units for that other one underneath. Kilopascals divided by mole, Kelvin, decimeters cubed times kilopascals. So their volume units are decimeters cubed, pressure units are kilopascals, and then moles Kelvin. Yes.
Is that times atmosphere?
Yeah, it's like liters times atmospheres over moles times Kelvin. That's the unit. You won't ever have to write out the unit. The reason that you know the unit, or I think it's important for you to see it, is that you see the units that have to be in place for this constant to work. Use the ideal gas law when we're only giving one set of conditions. So here's our volume, here's our pressure, our temperature, here's our moles, whatever. But this is not a before and an after, right? The combined gas law, Boyle's law, Charles' law, Guy-Lussac's, those are all, here's some change in our gas. But ideal gas law is just, here's what's happening, right? Tell me about it. Okay, R is the constant. You know what it is. You will not have to solve for R, so you don't have to write that part down. That's just something to think about. You'll be given what you need except for one missing variable. Okay, so the only thing you really need to know about ideal gas law is that you are using this when you're only given one set of variables. Okay, this is not a change in type of scenario, right? It's just here's the temperature, here's the pressure, volume, whatever. Okay? Let's try one. Calculate the pressure in atmospheres of 0.413 moles of helium at 16 degrees that occupies a volume of 3.25 liters. Okay, is there anything that jumps out at you in terms of units? Or Celsius. So we need to convert Celsius to Kelvin. So I do that by adding 273. And I get 289. So then I set up the ideal gas law. PV equals nRT. I'm solving for pressure, so I just leave that as a P. My volume is 3.25. N equals 0.413. R value we always know. Is that about what you had? Okay. I multiplied this whole side together, right? It's N times R times T, right? All of this is a multiplication term. So I multiplied the whole right side, and then I divided out my 3.25 on the left. So I divided out my 3.25 on the right. I got about 0.3015 atmospheres. Find the volume of 85 grams of oxygen gas at 25 degrees Celsius and 104.5 kilopascals. So do we see a couple issues with this? What's the first issue we see? It's in grams, and we need it to be in moles, okay? So we do that with just an easy T-chart, right? 85 grams, right? I want to go from grams to moles of O2. Moles always gets the 1, and then the molar mass of O2, not just O, right? 16 times 2, so 32, right? That's really important. We're so used to oxygen just being 16. When it's oxygen gas, it's got to be 32. So 85 divided by 32. That means that's our number of moles, right? So that's N. And that could round up to a 6, but whatever, I just did. Okay, we have our temperature, 25 plus 273. And then what unit, or what variable does this go with? Kilopascals. It's pressure, but we need to do what to it? We need to change it to atmospheres, right? We could use our other R value, but that means we would need our volume in decimeters cubed. We need our temperature in Kelvin. We need moles. I mean, so you could use that one if you wanted to, but I prefer to just put in atmosphere. So pressure, I would take 104.5 kPa. And what's my conversion factor between atmospheres and kilopascals? Good. 101.325. Is everyone seeing where we got that number at? Hopefully you wrote that down on your equation sheet or somewhere around there. Okay, so now I've got N, P, T. I'm solving for volume, and I always know R. Okay, so I'll go 1.03 P times V equals N times R times T. Anybody have an answer already? What'd you have? Perfect. Around 62.9. I had 62.86, but that's just depending on if you rounded early or not. Is that about what we had? Somewhere in there? Uh-huh.
So would that be liters?
That's right. Right. Since we used this R value, our volume has to be liters. Okay? If you had chose to keep it in kilopascals and use the other R value, your answer would have been in decimeters cubed, which I just don't think is that applicable of a unit. We don't use it that often is what I'm saying. Questions about that one? All right, I want you to try this one on your own. Is that what you had? Or close to that? Good. So the conversion of your pressure unit comes at the very end, right? You don't convert that until the very end because your answer will come out in atmospheres. Then you just convert from there to millimeters of mercury. Okay, questions about that? Okay. We're going to look at gas stoichiometry now. Gas stoichiometry is just regular stoichiometry, except you might be converting from moles to liters, which is why I gave you that 1 mole to 22.4 liter conversion. Okay? Okay, so to start this problem, like any stoichiometry problem, we need a balanced chemical formula. Right? We have to have a chemical reaction, because if we don't have the mole ratio. We can't do stoichiometry without that balanced chemical reaction. Okay? So how many grams of Al2O3 are formed from 15 liters of O2? Right? So here is our balanced chemical reaction. Right? I gave you your reaction. So Write that down if you need to, whatever. We're looking for grams. Oops. There you go. We're looking for grams from 15 liters. Start with what we know, 15 liters of O2. We need to get from liters of O2 somehow to grams of Al2O3. Okay, so what's got to be my first step? Liters to what? Liters to grams. We don't know how many grams of O2 are in a liter, right? But we do know how many moles are in 22.4 liters, right? We're going to use that conversion. So if I want to get rid of liters of O2 and go to moles, I know 1 mole is equal to 22.4 liters. Okay, so I've canceled liters. Now if I stopped here, I'd be in moles of O2, which is not what I need, right? Now I need to go from moles of O2 to what? To moles of Al2O3. So here's the only place that the moles doesn't get the 1, right? This number comes from the balanced chemical reaction. So what number goes here? 3, right? And what number goes here? 2, right? From our Al2O3. Okay. So I've canceled moles. Now I need to go moles of Al2O3 to grams of Al2O3. Okay, 1 mole. And then what goes here with grams? Molar mass. Okay, so go ahead and calculate that if you haven't already. Okay, what was our molar mass of Al2O3? 102. Okay. Making our final about 45.5 grams. Okay, so do we see the process for gas stoichiometry? Right, the only new conversion factor we get is to go from liters to moles, right? And moles still gets the 1 there. So I gave you that 22.4 in like our first slide, and that's just a conversion factor called Avogadro's principle. Okay, so 1 mole of any gas at STP, so you need to make that specification. 1 mole of any gas at STP equals 22.4 liters. It doesn't matter what gas it is, really big one, really small, whatever, but it equals 22.4 liters. Okay. We will find ways around that with other calculations, but the simple conversion here is with 22.4 at STP. How many liters of water can be made from 6 grams of H2 at STP? Now you're kind of going backwards. Okay, I'm going to use the same balance formula now to give you a question that doesn't happen at STP. So let me clear off this question, and I'll write a new one. Okay, how many grams of O2 will I need to make 3.0 liters of H2O. Okay, and we're going to assume this takes place at 298 Kelvin. Okay, so not at STP, right? This is at room temp. Because my system is not taking place at room temp, I can't trust the 1 mole equals 22.4 liters ratio. And so what I need to do is I need to find out if this is liters of water that I want to make. I want to find out how many moles of water is that, right? How many moles of water do I need to make? And so the way I do that is using the ideal gas law, right? Because my liters conversion won't work in stoichiometry, because it's not at STP, I can't use that in my T-chart, right? I can't use 22.4 in my T-chart at all. So I have to find another way to convert my liters to moles. And so I use the ideal gas law. So for water, sorry, we need to say it's at 1 atmosphere also. Okay? So for water, my pressure is 1, my temperature is 298. R we know, volume is 3.0, and we want to find out how many moles it takes, right? Or how many moles of water am I producing? And then we can do an easy stoichiometry calculation saying, if I want to make X moles of water, how many grams of oxygen do I need? Right? So we take the temperature and the pressure components of it into our ideal gas law, and then we can just do a regular stoichiometry problem after that. Okay, so I say P times V equals N times R times T. So what this is saying is that under these conditions of temperature and pressure, 3.0 liters of water gives us 8.16 moles of water. Right? Is that right? Is that what you had? I don't feel like that's right. That's way too big. I divided the wrong way. Okay, that's a problem. Whew, all right. So tell me what it should be. I should do 3 divided by my... Okay, all right. Sorry. 0.122. There we go. Sorry. Okay. So N equals 0.12. We'll just go 0.123 moles. That makes a little bit more sense. Okay. So now this is how much water will be produced in moles, right? 3 liters of water at this condition is 0.122 moles of water. So now I'm going to take my T-chart basically with what I know, 0.123 moles of water. And I'm going to go moles of water to moles of O2, moles of O2 to grams of O2. Right? That's it. Then it's just a simple stoichiometry calculation.